Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
Oregon and Washington have been identified by the U.S. Geological Survey as very high threat volcanoes.
The discovery began with a series of strange seismic patterns rippling quietly beneath the Earth's surface between Yellowstone National Park and the high desert expanses of northern Utah. At first, geologists monitoring the region dismissed the tremors as typical background activity in one of the most geologically dynamic parts of North America. Yellowstone has long been known as a supervolcano, a cauldron of subterranean power with a caldera capable of massive eruptions. But this time, something was different. Deep Earth sensors started detecting abnormal resonance signals, a kind of underground vibration that didn't match the usual volcanic or tectonic behavior. As more data poured in, the anomaly pointed to something astonishing: an extensive, previously undetected magma tunnel stretching between Yellowstone and Utah. The implications were staggering. Before we start, smash the like and subscribe buttons for more updates. Immediately, a flurry of research teams mobilized to analyze the nature of this subterranean feature. Magma tunnels, channels where molten rock can flow through the Earth's crust, are not unheard of in volcanic zones. But what shocked scientists was the size, direction, and energy readings from this one. This was not a narrow lava tube or a dormant fissure. It was a vast, active conduit, seething with superheated magma moving beneath the Earth's crust at incredible pressure. Using a combination of satellite thermal imaging, deep seismic readings, and magnetotelluric data, researchers traced the tunnel's route as it stretched from the edge of the Yellowstone caldera, winding its way underground through mountainous terrain and terminating near the Uinta Basin in Utah. The geological community was stunned. This tunnel, hidden miles below the surface, represented a literal pipeline of magma bridging two regions previously not thought to be directly connected by active volcanic structures. Yellowstone, long monitored as a potential source of a super eruption, now seemed to have a volcanic lifeline extending far beyond its known boundaries. What once was thought of as a relatively contained volcanic system was suddenly revealed to be more complex, more interconnected, and potentially more volatile. The declaration of a red alert followed quickly after confirmation of the tunnel's activity. This is the highest warning level in geologic monitoring, reserved for scenarios involving significant volcanic unrest with potential immediate consequences. It doesn't mean an eruption is guaranteed, but it signals that the system has entered a phase where magma movement is increasing rapidly and unpredictably. The fact that the magma wasn't just rising vertically from Yellowstone, but was instead traveling laterally across vast distances, hinted at dynamic shifts within the Earth's crust. The crust beneath this region of the continent, already riddled with fault lines, uplift zones, and heat anomalies, may now be undergoing accelerated transformation. Geologists who had spent years studying the Yellowstone hotspot began reevaluating their models. Traditionally, Yellowstone's volcanic system was seen as relatively isolated, fed by a plume of magma rising from deep within the mantle. But with this tunnel, it appears that the system is capable of expanding its influence laterally, like a living organism stretching out its limbs. This newly discovered magma passage might act as a pressure release valve, or more alarmingly, as a fuse. If pressures in the magma chamber beneath Yellowstone rise too high, the energy could divert into this tunnel, pushing molten rock into previously dormant or less active zones in Utah. The Uinta Basin, where the tunnel seems to end, or possibly continue further, has never been classified as a major volcanic area. It is geologically significant, with complex sedimentary layering and active fault systems, but there's no modern history of large-scale volcanic activity. However, the presence of hot springs, geothermal vents, and gas seeps in parts of the region now take on a far more ominous meaning. These surface features, once considered minor curiosities, might be surface expressions of deeper volcanic undercurrents. Now, they could serve as pressure release points, or worse, weak spots where magma could eventually breach the surface. The red alert not only served as a call to scientific attention, but also as a cautionary signal to civil authorities and emergency planners across the Intermountain West. The entire region from Wyoming through Idaho and into Utah is seismically and volcanically sensitive. The discovery of a vast magma tunnel threading its way through this landscape adds a new layer of risk and complexity. Not only must geologists now model the behavior of Yellowstone's caldera and magma chamber, but they also must assess the dynamics of magma flow through this newly revealed corridor. Pressure buildup in magma tunnels can result in unpredictable changes in volcanic behavior. Depending on the composition of the magma, the tunnel could harden and seal itself, or more dangerously, it could act as a low-resistance path for magma to surge into weaker crustal areas. If the magma is particularly rich in volatile gases, as some early samples suggest, any eruption triggered along the tunnel could be explosive. Such an eruption wouldn't need to come from Yellowstone itself. Instead, a new vent could open in Utah or anywhere along the tunnel's route. That possibility rewrites the entire map of volcanic hazard zones in the western United States. Another deeply concerning implication involves crustal deformation. Satellite-based INSAR imaging revealed that areas along the projected tunnel path are experiencing uplift. Subtle, but measurable. The ground is rising, hinting that pressure from below is pushing upward. This is a classic precursor to volcanic activity. And while uplift doesn't always lead to eruptions, it's one of the earliest and most important warning signs. The fact that uplift is occurring far from the Yellowstone caldera suggests the tunnel is already active in transferring energy and pressure laterally. The magma within the tunnel is also unusually hot, based on thermal data extrapolated from deep Earth readings. This temperature anomaly could indicate fresh influxes of mantle-sourced magma, rich in volatiles and heat. Such magma can melt surrounding rock more rapidly, expanding the tunnel and potentially accelerating the timeline for volcanic surface activity. The chemistry of the magma is also under intense scrutiny. Initial readings point to a complex mixture, andesitic in some sections and basaltic in others, suggesting the tunnel may be interacting with multiple types of crust along its length, each with its own volatile potential. All this unfolding geological drama paints a picture of a region in flux, where ancient forces are stirring in new and unpredictable ways. The red alert doesn't just warn of a possible eruption, it signifies a shift in the way Earth's subterranean systems are communicating. For the first time in recorded history, there is compelling evidence of an active magma tunnel connecting two major regions of the American West, with the potential to alter landscapes, ecosystems, and even climate, should an eruption occur. The interconnectedness revealed by this discovery also raises broader questions about the structure of the North American plate and the deeper mantle plume suspected to underlie Yellowstone. Could there be more such tunnels, threading their way through the crust, hidden until now by the limitations of earlier technology? This magma tunnel could be just one part of a vast volcanic network operating out of sight, a hidden circulatory system of molten rock that ebbs and flows beneath the surface, shaping continents and triggering cataclysms. For geologists, this discovery represents both a breakthrough and a burden. Understanding the behavior of a dynamic system on this scale is incredibly complex. Each data point, each seismic ripple must be analyzed in context and models updated in real time. Computer simulations now have to account for lateral magma flow, variable crustal thickness, and unpredictable chemical interactions. It's a daunting task, but one that could yield profound insights into how Earth's inner heat manifests on the surface, and how close humanity might be to witnessing a once-in-a-millennia event. One of the more immediate challenges is assessing the risk to populations living in proximity to the tunnel's suspected path. Towns and cities in Idaho and Utah sit atop or near these newly suspect zones. In the past, emergency planning focused almost exclusively on the potential eruption of the Yellowstone supervolcano. Now, new scenarios must be considered: localized eruptions in unexpected areas, ground collapse due to magma migration, toxic gas emissions, or even large-scale geothermal instability. While no evacuations have been ordered, officials have begun issuing advisories and increasing geological monitoring stations in strategic locations. There is also renewed interest in ancient geologic records from the region. Could similar magma tunnels have formed in the past, possibly contributing to prehistoric eruptions or unexplained crustal shifts? Layers of ancient ash found in sediment cores across Utah and Idaho, once attributed to distant volcanoes, may need to be reanalyzed. These layers could represent forgotten or misidentified eruptions from a long-dormant branch of the Yellowstone system, one that has now awakened. This discovery has created ripples well beyond the geological community. Climate scientists are beginning to model how a potential eruption, whether from Yellowstone or a new vent along the tunnel, could affect global temperatures. Even a moderate eruption could inject vast amounts of ash and sulfur dioxide into the atmosphere, potentially lowering temperatures and disrupting weather patterns for years. Agricultural agencies, meanwhile, are considering contingency plans in the event that air or soil becomes contaminated. The stakes are no longer theoretical. The Earth has shown a new card, and it may be one with long-reaching consequences. But while the discovery of the magma tunnel has introduced a host of new dangers, it has also provided an unprecedented opportunity. Never before have scientists had the chance to monitor the birth, or perhaps the awakening, of a new volcanic system in real time. With modern technology, from satellite surveillance to AI-enhanced seismic analysis, humanity is uniquely positioned to observe and learn from these developments in ways that were unimaginable even a few decades ago. Each day brings new data, new puzzles, and new urgency. At its core, the revelation of the Yellowstone-Utah magma tunnel is a reminder of Earth's raw power, still largely hidden from view yet capable of transforming the planet without warning. It challenges assumptions about the rigidity of tectonic boundaries, the containment of volcanic systems, and the permanence of the landscapes we inhabit. Beneath the forests, deserts, and mountains of the American West, something ancient is moving, slowly, inexorably, with heat and purpose. The red alert stands not only as a warning, but as a symbol of the ongoing mystery beneath our feet, where fire carves its secret paths through stone, and where even the ground we walk on is never truly still. As the implications of the newly discovered magma tunnel began to unfold, attention shifted toward its potential influence on the broader geological systems of the western United States. The tunnel's presence adds an entirely new dimension to understanding the interactions between tectonic plates, mantle plumes, and crustal dynamics in the region. Seismologists are now investigating whether this tunnel acts as more than a passive conduit for molten rock. Some suspect it could be influencing fault lines, particularly those in the Basin and Range province, which spans from eastern California through Nevada and into western Utah. This area is already under tectonic strain due to the stretching of the North American plate, a process responsible for the region's characteristic block faulting and elevated plateaus. Now, the presence of an active magma corridor running beneath it raises the possibility that subterranean magma pressures could be exacerbating tectonic tension. This introduces a risk of heightened seismic activity, not necessarily tied to volcanic eruptions, but to earthquakes triggered by stress redistribution in the crust. In such a scenario, tremors and faults that were once considered relatively benign might now pose increased risk due to indirect magma influence. Furthermore, the potential heat output of such a large underground magma system could be affecting subterranean aquifers and hydrothermal systems. Aquifers beneath Utah, Idaho, and Wyoming are essential sources of fresh water for agriculture and municipalities. If the magma tunnel's heat flux alters the thermal gradient in these regions, it could trigger thermal expansion in underground water sources, leading to changes in pressure and volume that might manifest as geyser activity, new hot springs, or even hydrothermal explosions. This is not merely speculative. Historically, such interactions have led to catastrophic bursts, as seen in areas like New Zealand's Taupo volcanic zone. The discovery also invites deeper questions about what lies even farther underground. While the tunnel was found using seismic tomography and magnetic data, those tools only provide indirect glimpses into the Earth's crust and upper mantle. Some geophysicists now theorize that the tunnel might be one arm of a much larger magmatic network branching from a deep mantle plume. If that's the case, then Yellowstone's volcanic system may not be the singular, isolated supervolcano it was once believed to be. Instead, it could be a surface expression of a broader mantle upwelling that stretches beneath much of the Intermountain West. This network theory is currently being tested with higher resolution seismic imaging and deep crustal surveys. If confirmed, it would mark a paradigm shift in our understanding of Western North America's volcanology. The region's geologic past, its calderas, ancient lava flows, and uplifted mountain ranges, could then be re-evaluated through the lens of this newly revealed subsurface architecture. Every extinct volcano, every fossilized ash bed might represent not a localized event, but an outflow point of a migrating or pulsating magmatic force that now appears to be active once more. Another dimension of the discovery that is garnering significant scientific attention involves the role of volatile compounds in magma transport. Volatiles such as water vapor, carbon dioxide, and sulfur dioxide are key drivers of explosive volcanic eruptions. Data collected from gas emissions near both ends of the tunnel indicate elevated levels of these volatiles in surface vents, an indirect sign that the magma below is highly charged with explosive potential. The chemical composition of gas emissions is being studied carefully, with mobile gas sensors and airborne sampling missions deployed to trace any fluctuations that might precede magma movement toward the surface. These emissions also pose environmental and health concerns. Volcanic gases can contaminate the air and water, causing respiratory problems in humans and animals, acidifying water supplies, and damaging crops. In regions near the projected tunnel path, local authorities have initiated baseline measurements of air quality and water pH to track any deviations that might signal rising volcanic gases. In the event of continued magma pressurization, gas surges could precede surface eruptions or ground venting, endangering nearby communities even before any lava reaches the surface. Even more intriguing is the possibility that this magma tunnel is not static. Researchers are entertaining the idea that it might be expanding, branching, or even shifting. Magma doesn't move like water through a pipe. It can fracture rock, change direction, and create new paths of least resistance depending on the surrounding geology. This dynamic quality makes long-term forecasting extremely difficult. Areas currently considered safe could find themselves suddenly sitting atop new volcanic feeders if the tunnel evolves or forks under pressure. To improve situational awareness, a new generation of deep monitoring stations is being deployed throughout the tunnel's suspected path. These stations are equipped with magnetometers, gravimeters, seismometers, and temperature probes to create a continuous picture of underground activity. High-frequency tremors, magnetic anomalies, and changes in gravity can all provide early clues to subsurface shifts. Some of these stations are being placed in remote, high-altitude terrain that has never been thoroughly monitored before. Drones and autonomous vehicles are playing a critical role in deploying and maintaining these instruments in areas inaccessible by foot or vehicle. Another layer of investigation is being driven by machine learning and artificial intelligence. Decades of geophysical data are now being fed into models capable of detecting patterns that human analysts might overlook. These algorithms can correlate microseismic tremors with subtle crustal movements or rising gas levels to predict where magma might be heading. Some early outputs from these systems have already revealed surprising trends. Slow pulses of seismic energy migrating southward from Yellowstone, echoed days later by gas emissions near Utah's geothermal zones. These correlations, though still under scrutiny, could represent a form of magma messaging, indications of pressure fronts moving through the tunnel system. In parallel, attention has turned to the potential impact of such a subterranean system on geothermal resources. Utah and Idaho already harness geothermal energy, but if the magma tunnel proves to be stable and accessible in certain areas, it could represent one of the largest untapped sources of clean energy in North America. However, exploiting it comes with high risk. Drilling into or near an active magma tunnel could destabilize underground pressure balances, triggering seismic events or unwanted eruptions. This has sparked a heated debate between energy developers and geologists over whether the risks are worth the potential energy yield. Scientific institutions across the world are now collaborating to study the tunnel's composition and evolution. A number of international teams specializing in volcanology, deep earth imaging, and mantle dynamics have expressed interest in contributing to ongoing research. Some are even proposing drilling into peripheral areas of the tunnel, not into the magma itself, but into surrounding rock formations to retrieve core samples that could offer clues about the age, temperature, and chemical interactions happening within the crust. These samples may help determine how long the tunnel has existed and whether it is a recent formation or a reawakened relic of a prehistoric magmatic cycle. Meanwhile, satellites continue to observe from above, capturing high-resolution thermal images, radar interferometry, and visual documentation of subtle surface changes. From space, the Earth seems calm, but minute fluctuations in ground temperature and shape hint at the brewing intensity below. In regions where the tunnel bends or widens, faint surface anomalies barely visible to the naked eye are now being documented, tracked, and mapped against underground models. Some of these anomalies are mere centimeters in elevation change, Yet they suggest magma is pooling or slowing in these regions, potentially setting the stage for future uplift or fracture. Scientists are also watching for unusual biological activity. In ecosystems with volcanic influence, plants and animals often exhibit subtle changes in behavior before geological events. Near the southern end of the tunnel, wildlife biologists have reported strange migratory patterns in elk and deer herds, along with changes in the blooming cycles of certain high desert flora. Whether these are coincidental or biologically driven responses to deep Earth signals is still being investigated, but historically, such signs have often preceded eruptions and earthquakes. As this complex narrative continues to unfold, what becomes most apparent is the vastness of what remains unknown. The Earth, despite all modern tools and technology, retains its secrets. A single discovery, a magma tunnel hidden for millennia, has upended assumptions, redrawn hazard maps, and forced a re-evaluation of long-standing theories. It is a sobering reminder that the planet is alive in ways we are only beginning to comprehend. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the magma tunnel? Will Yellowstone erupt sooner than expected? We want to hear from you. Thank you for watching and see you next time.